I want to introduce a couple data structures to you, which are sets and maps, and that's because these two data structures are commonly implemented using binary search trees. So a set is pretty straightforward. It's some set of values, right? Like 1, 2, 3. It's pretty similar just to having like an array, but usually the word set implies that there's some other underlying data structure being used, not an array. One implementation could be a binary search tree. So if we have the values 1, 2, 3, but they're in a binary search tree, it could look something like this. And the advantage of having a set implemented with a binary search tree rather than like an array is that we can search for values, insert and remove values in log n time. So that's pretty straightforward. Now I also want to introduce to you the idea of a map. Let's first understand why it's important. Suppose we had something like a phone book where it's sorted in alphabetical order from A to Z, right? And that's based on the name of the person. Now, most people don't use phone books anymore, but I think it serves as a good example. So we have a bunch of names in the phone book, something like this. We could have Alice, Brad, Colin. Now notice these are in alphabetical order. But what's important here is that for every name, we don't just care about every single name. Every name is mapped to something else. That's where the word map comes from. In this case, every name is mapped to some number, some phone number. Let's just put 1, 2, 3 for simplicity. And, Brad could have some other number, 4, 5, 6. And then Colin could have something else. Now, the idea here is that we want to store all this information, but we want to sort by the name. But for every name, we want to have some other information. We call this a key value pairing. So we map a key to a value, and the data structure is typically sorted by the key. So in our case, when we had a binary tree, originally we had nodes that just had key values. That's our simple case where we have a set. But using a map, each node could have a key, which is what would decide how to structure the binary tree in terms of sorting it. But each node could also have an associated value, which in this case would be like a phone number. The value could even be its own object if we wanted it to be. Right? It could be multiple values. It could be, all the information about the person, their phone number, their social security, their email, a bunch of stuff. The idea, though, is that we're sorting by the key. So if we want to search for somebody in the phone book, it's efficient for us to do so by searching the names. We can do that in log n time because we know it's sorted by the name. But once we have that name, we have all the information about the person, aka the value. So this is one way of implementing sets and maps. Using binary search trees, we can implement sets and maps. So the binary search tree is the underlying data structure. It's similar to how we talked about stacks earlier. Stacks are kind of the interface or also the data structure we can push and pop, but underneath that, it's implemented with dynamic arrays. Similar to how queues are implemented with linked lists. Sometimes they can also be implemented with dynamic arrays as well. But sets and maps, they can be implemented with other data structures, which we'll be talking about later. One example is hash maps and hash sets. But like I said, we'll talk about that later. Depending on how you implement these, like which data structure you use, whether it's a BST or a hash map, there can be different trade-offs. We talked about the time complexities of binary search trees already. Now, depending on what language you're using, these can have different names. But for binary search trees, it's typically called an ordered set or a tree set. And for maps, it's called an ordered map or a tree map. And just to take a quick look at what it looks like in some common languages, the good thing about Java is it has a built-in tree map. So you can create a tree map where the key is a string and the value is a string. We could also use integers and other things as well. C++ also has native tree maps. They're just called maps in this case. The downside about Python and JavaScript, they don't really have native tree maps. You can install other packages. For example, in Python, you can use the sorted dict package, and this is essentially a tree map under the hood. For JavaScript, there are other packages as well, which implement tree maps. Now, in terms of real interviews, it's most common that you're actually implementing a tree map or running some algorithm on a tree map, like searching or inserting or something like that. It's not super common that you actually need a tree map, like the built-in tree map at least. But if you run into that case and you're using Python or JavaScript, most likely your interviewer will let you assume that some object or some interface like that already exists and you can use it, and you don't necessarily have to implement it from scratch if that's not what the problem is. Now, sometimes the interview question itself might be to implement, the data structure or parts of it from scratch. But what's most important is understanding what kind of interface a tree map would have. Like the things that we talked about. You can insert, you can remove, you can search, you can iterate, you can do the in-order traversal, and understanding the associated time complexities of those operations, which we talked about.